Hello, this is Mr. Jackson with Physics, and today I want to talk about the concept of the idea. I want to introduce it on free fall. Free fall is basically just acceleration, but it is acceleration that is due to gravity. And so the Earth, as it pulls things to the ground, things accelerate towards the ground, okay? And so as we talk about this, I just want to give you a couple scenarios that help you answer questions better. So we want to understand that we have two ideas. We have to understand that when we mention the word drop, so something is dropped, okay? We want to know that our speed, initial speed, is going to be 0 meters per second. But at the same time, we now have a new idea. We now have a value for acceleration. An acceleration that is due to gravity, when something is dropped, we can always plug in with this value. It'll be 9.81 meters per second squared. That is the accepted value for what an object will accelerate as it drops. So if you drop something, it begins to speed up and go faster and faster and faster. Okay? So its original speed will be 0, but then once it goes a second, it will go and fall now. So now it'll be at a new speed of 9.81 meters per second. And then after 2 seconds, its speed will be 19.6 meters per second. And then the speed will then increase another 9.81 and be at 29.4 meters per second. And then it will get even faster. As long as it keeps going, it has room, it will keep increasing in speed, and its increase will be the same, 9.81 meters per second squared, okay? But remember, be careful. We have defined upward as positive. So that means that when an object falls downward, it's not decelerating, but its directional component is negative. So it's falling downward at negative 9.8 meters per second squared. But this is the speed increases that will occur. Okay? So we have a dropping situation for free fall. And in these problems, let's do a little quick idea. Let's do this idea. Let's say we have this person that is dropping a ball off of a building, and this ball begins to fall faster and faster and faster until it finally reaches the ground. Now at the ground, I know it hits the ground, it'll stop, but we're in just microseconds before it hits the ground. What is that object's speed going to be? So let's say this is our question. Let's say we have a 50-meter tall building, and so if I want to figure out what will be the speed right here, okay, then we just do our list like we've been doing. I've taught you in acceleration equations, VF, V0, A, D, and T. Our distance is 50 meters, okay? And because all I said was dropped, I actually can put this information right into my given list. So I can put in there 9.81 meters per second squared, okay? And then what happens is I V0, because it's dropped, is 0, and I want to find that equation. So remember, we use our missing information, so to find this VF. So that leads me to the equation with no time, VF squared equals VI squared plus 2AD. Now, since it's downward, even though I know it's increasing in speed, I'm going to use this as negative and the distance as negative, but then what's a negative times a negative? It's positive, so they'll cancel each other out. But downward is negative when it comes to positive physics, so we got to keep that in mind. So all I'm going to have to do is put my x here, I'm going to square it, equals 0 squared, which won't have any effect on my problem, plus 2 times negative 9.81 meters per second squared times negative, because it's downward, we're falling downward, 50 meters. And then I just have to plug my numbers in. We have 2 times 9, and negative times negative is positive, so I'm going to ignore the negatives. So 2 times 9.81 equals times 50 equals, and that equals x squared, 981. Okay. And I want to take the square root of that number. So square root, shift square root of 981 equals 31.3 meters per second squared. Oops, sorry, meter per second, not squared. My fault. It is not a squared number. This is a speed, so it does not get any squared information, okay? So that's a dropping problem, and when things are dropped during free fall, we have now more information we can add to our list due to that, okay? So let's do another one. Let's talk about when an object is going to free fall, but this time it's being shot upward. And so when things are shot upward, or okay, what I want to understand is that an object, let's say we have a cannon. So here's my cannon pointing upward, okay? And it's going to shoot an object, a cannonball higher, and then reaches the top, and then it's going to turn around and fall down to the ground again, increasing in distance as it goes, and finally return to the same position as it's been shot from, okay? And so what happens is this cannon, okay, which is shooting up, so it's a cannon, and it's shooting upward and back down. I want to figure out, some information about that. I want you to understand as it goes up, it is decelerating. A is negative, but it's positive, 9.8 meters per second squared, okay? But it's also slowing down. At the top, the final speed is 0, okay? And the distance it rises is the same as distance it falls. But if I wanted to look at this side of the equation, so I can kind of divide it, if I look at this side as the top, but if I want to look going downward, then it starts all over again with the same process. V0 is 0. And then A is 9.81 meters per second squared. So I start to fall into the same information. And so here going up, the distances are positive, but here the distances are negative going down. So I just got to make sure I keep the right signs, so positive and positive, so we know it works out. So we got to be careful on that. But shooting upward, we have an object going up. At the top, it stops. But if I want to look at this side of the equation, at the bottom, it's starting to fall downward. And so here, my initial speed is from the cannon. Here, it then falls down, final speed. It will fall down as long as there's no drag, which means air friction. It will fall down at the same speed as the cannon, again, because it'll hit the ground at the same speed it went up, okay? So these are the ideas I want you to realize. When something's being shot into the air, it slows to a stop, and at the top it microscopically stops and then turns around and comes back down. So there's a change in directions, and speeds can be, so you can either analyze a problem from this side or this side, okay? And I want to talk about that. So the last thing I need to talk about is drag. And drag is the idea that when things drop in the earth, they are pulled down at 9.8, but there is air particles everywhere around in the earth, and they hit against stuff and they push back up and they slow things down. But it is not noticeable for short distances. Like off of a building, you would never see a lot of air drag. But you throw something out of a helicopter or an airplane way up in the air, things will slow down. We are not going to consider drag in our problems. But what I want you to know is drag is important if things are light. So drag is important for very light objects. Okay? Things that have a large area. And so I'm going to give you an example of that here really quick, okay? So I'm going to do a quick demonstration and show you what I'm talking about. Okay, so I really want to show you something right here. I have a piece of paper and a ball. If I drop them, we see that the ball falls and hits first because there's too much drag on the paper. But if I take the paper and crumple it up and remove its size but not its weight, and I know that right now the ball is still way heavier, but truth is that if I can remove any air resistance or drag and then drop the two, they will hit at the exact same moment. So that proves that we know that the drag is only important on small objects with large air resistance. So remember that, okay? So that's very, very important. So what I want you to know, and what's important is, drag is not important. All objects fall at the same rate. So when it comes to free fall, as long as our objects are light objects with very small surface area, when they're not light, then they're going to fall at the same rate. So we're not going to worry about drag right now in this unit. So we can just keep using the same number over and over again, okay? And so I just wanted to point that out. And I gave you a couple of videos that they actually dropped something on the moon without atmospheric air, and it fell at the same rate, a feather and a hammer. It was awesome. They did it on the moon to prove it to be true. So I just wanted to point out what the idea, they mentioned do not consider drag. They're saying we're not going to worry about objects that are going to be affected by our air. They're just going to fall nice and freely at this rate. Okay? And that is a short rendition of how we can use free fall in our acceleration problems.